Hello, I'm Professor Roger Congleton, and this is Econ 701 at WVU during the fall of 2024. So today what I'm going to do is do two lectures. First I'm going to do a mini lecture on how to derive consumer demand curve from an abstract utility function. And then next, in a separate recording, I'm going to introduce the theory of supply, both geometrically and using explicit functional forms. I'm doing this because I contracted COVID last week and I didn't want to spread my germs to the class this week. And so if you catch COVID, you can't blame it on me. I personally blame it on a student who was standing in the hallway last week coughing up a storm not too far from my office. But of course, there's no way to prove that. That's just an inference drawn using kind of statistical reasoning, I suppose. All right, so for those of you who have not done these recorded lectures before, you should treat them like a course in, an in-person course. Okay, in-person lecture. So you should take notes. And in my case, when I record a lecture, I just talk pretty much straight through the lecture. And so if you want to take notes, you have to hit pause. Okay, hit pause, and then hit play when you've written down what you think is useful. Okay, so I've written a bunch of stuff on the whiteboard. If I were in class, it would have taken me, 5 minutes or so to put that material on the board. And then I would wait another 5 minutes while you copy it down. Okay, but if you're copying it down, just hit pause, and then I'll proceed when you hit play again. So let's begin by thinking a little bit about what a demand function is. A demand function is some kind of function from prices into quantity. Now, the function can have a bunch of other variables in it, like the prices of other goods, consumer income, something about the characteristic of the good itself, some quality index or something of that sort. So you can imagine that the function has a whole series of variables, not just price. And that is part of the power of doing these kinds of models using calculus. And also one of the advantages of using kind of abstract functions, because you don't commit to a particular relationship between the variables in the same way that you do when you assume a concrete functional form like the Cobb-Douglas or the exponential multiplicative extension of that. So you'll get much more general results if you can get any results at all. Sometimes as you add complexities, you also add ambiguity into the model results. Structure is clear, okay, in terms of what variables are included, and some basic characteristics of the assumed relationships are also clear, okay. But sometimes, your conclusions about comparative statics aren't as sharp as you'd hope they would be in a model. Okay, in this model, turns out the implications are pretty easy to work out, and they are the ones that we as economists think are intuitively obvious. They're not intuitively obvious to everyone, okay, but most people who've made it this far in an academic program find them completely plausible and intuitive, and so you won't be surprised by anything that turns up today. You may learn a little bit of math, though. Okay, so the implicit function, abstract functional form of an abstract functional form of a utility function is just something like this. There is a function that maps combinations of x and y into utility levels. Utility can be thought of as kind of an underlying coherent, internally consistent objective that an individual might have, and that such an objective might be happiness or satisfaction, success in some sense, or any other term you might want to think of. I mean, people have different motivations, I suppose, to some extent. So if x and y are both goods, then the partial derivatives of both x and y with respect to the utility are positive. You get more of x, you're better off. Get more of y, you're better off. Right, so that assumption rules out satiety, something we talked about in the lecture last week on Thursday. The other assumption we make is that the second derivative is negative in both cases. That is, both goods are subject to diminishing marginal utility. And then another assumption, which doesn't have as much in the way of economic meaning, is that I'm going to make today is that the cross partials are greater than 0. So what does that mean? That means that if you have more y, the marginal utility of x goes up. Right, so that implies that somehow having more y makes x more useful, more attractive, more enjoyable. And there are lots of cases where that seems entirely plausible. For example, if you're not starving, in some sense, you're not, if you're then drinking something might be more pleasant than if you are. Okay, so if this was food and this from water, you might think, okay, well, the more food you have, the more pleasant the water tastes, in some sense. And vice versa, right? The more water you have, the more your thirst is quenched, the more pleasant it is to enjoy a sandwich. So the cross partial is not always logically or intuitively greater than 0, but it turns out that that cross partial is greater than 0, along with the other two assumptions about partial derivatives. That assumption is sufficient to make the utility function strictly concave. And if it's strictly concave, it can have at most one maximum. And so you've got a condition for establishing the existence of a function. The function we're interested in is this demand function. Okay, so we went through the Lagrange method last time using concrete functional forms of the exponential multiplicative variety. We showed how that particular optimization technique works great with that family of functions. And if you try other families of functions, you'll find that it doesn't work nearly as well. Okay, and often even with concrete functional forms, you cannot solve a system of Lagrange equations to determine what a demand function actually looks like. So that's a problem. Okay, I mean, in a sense, there's no real reason to fool around with explicit functional forms. Unless you can get a nice explicit representation of the functions you're actually interested in characterizing, like the demand function. And the technique, the Lagrange technique, is less useful for abstract functional forms because you basically never can solve for particular relationships. Although you can sometimes get qualitative results, like the sign of some derivative should be x, y, or z. It should be positive or negative, for example. And in a sense, what I'm doing today is consistent with that type of approach, where you use the multi-equation version of the implicit function theorem and implicit function differentiation rules within the context of Lagrange systems of equations that characterize a solution to a multi-dimensional problem. But what we're doing today is to kind of simplify things a bit. We're going to deal with a world where there are only two goods. We're going to deal with the case where there's an inequality budget constraint. You have so much money that you're going to spend, and you're going to spend it all on some combination of these two goods. You don't know how to divide that money up. Given all the other assumptions, the implication of the fact that both these goods have positive marginal utility over the whole range is that you'll spend all the money. And if that were not true, it's possible that you would be satiated before you got to the budget constraint, and you would just throw some money away rather than spend it. Okay, so the fact that you're going to spend all the money means that you're going to be on the budget constraint at the optimum. Okay. So the part of the utility function that's of greatest interest is that part that's right along the slice of the utility mountain above the budget line. Well, it turns out if you look at the budget constraint that you can write y as w minus pxx, which is w is what you got to spend, pxx is how much you spent on x. So this is money you got left over to spend on y. In the numerator, divide that by the price of y, that gives you the quantity of y you bought. Okay, so if we substitute that for y into the function, the utility function, we have an expression that looks like this, which is a bit, which looks a little complicated. It's not really very complicated compared to some things we'll see later in the semester. And so if we take a derivative with respect to x, it turns out we'll be able to characterize both x and y. Once we know x, we can just take that value of x, substitute it into this equation, and figure out what y star is. Right? Because if I know what x is, then I know how much money is left over to spend on y, and then if I divide that by the price of y, I know how many units of y I'm going to get. So it turns out that this equation has only one control variable in it. Right? In the choice setting has two control variables in it, x and y, and it has some parameters of the choice environment as well, including the utility function itself, but also px, py, and w, which are seem to be beyond the control of the individual making the choice, and so are not control variables, although they are parameters of the choice setting. So if we take a derivative of this term, this function, it turns out that the notation for what you get is the following. You get the derivative of the first variable, okay, du dx, plus the derivative of y with respect to x. Okay, well that's a composite function rule, and the way you get that is you define du dy first, and then dy dx second, and that's this term, minus px over py. Right, if you think of this term as y, take a derivative with respect to x, you can see that you could think of this term as w over py minus px over py times x. Well, only one of those two terms has an x in it, namely the minus px over py times x. And so when you take that derivative, it's pretty simple. It's just minus px over py, and that's that term. So it's pretty easy to characterize x star. Now this is really the marginal benefit, and this is the marginal cost of consuming x. Now notice the marginal cost of consuming x in this case is a reduction in your consumption of y. You're along that budget constraint, and as you move along the budget constraint, if you get more x, you're always going to have less y. Right? It's the nature of that constraint. And notice it's not just the number of units of y that you're giving up, which is kind of captured by this term. It's that dy dx term. But also the utility that you're losing from y. Right? So this expression is in terms of subjective values. This is a subjective advantage, benefit from having more x. This is a subjective cost of having more, of having to give up more y to get x. All right, so this is the marginal opportunity cost of x, and this is the marginal benefit of x. So it's one of the few places where a particular way of approaching the choice setting yields this kind of really neat microeconomic result that again, it's still marginal benefit equals marginal cost in a sense, but the marginal cost notion is now more sophisticated. It's taking account of the thing you're giving up rather than just its cost. Well, that's a zero function, right? If we're at x star, assuming there is such a thing, then this term will be zero, right? Marginal cost will equal marginal benefit. And so marginal benefit minus marginal cost will be zero. That's that minus term right there. And so we can use that as an h function in the implicit function theorem, right? And we've done that before, okay? But this time we're doing it in a little more general context, where it's not quite as obvious what's going on. So the implicit function theorem says, well, given any function that is always zero, okay, we can always take any single variable out of the string of variables included in that function, the h function, in our notation, and write that function as a function of all the other parameters. Okay, so the parameter we're most interested in is q at this point. We want to know what q star is, or x star, okay, in this case, because I'm using x's and y's. And if you look around for parameters, there's no y in this thing, right? There's no letter y anywhere in here. Okay, so y is not a control variable, is not a parameter of the problem, except insofar as it determines the relationship between this term and utility, at least notationally. And so you can write x star as a function of px, py, and w, the three parameters in the choice problem. All right, so having done that, we found the demand function, right? That's what this is. And we can also write y star really quickly as w minus px x star over py. Right, so in this way, with really just a couple of steps, we have characterized the demand function for x and the demand function for y. And of course, it's really just, 3 lines of calculus. Once you see this approach of looking at the slice along the budget line as being a way of analyzing the problem, and the fact that that substitution allows you to eliminate one of the control variables, namely y in this case, everything else is pretty straightforward. You do have to kind of learn how to write the notation, how to do these derivatives of implicit functions. That's not easy. It takes some practice, and you'll get lots of practice with that in the course. Okay, so I'm going to next take a look at some of the comparative statics of this thing. And a lot of the comparative statics, just as true of this first derivative, tend to look like notation. And that's because they basically are notation. Okay, so if I want to know the slope of the demand function, well, that's, what did I call that thing? It's dx star px, and it will be dh dpx over minus dh dx. Right, that's just the implicit function differentiation. Well, here's h. And the tricky part of this is remembering that these terms, these two partial derivatives, both have the same arguments as their parent functions. Right? So this thing here is really a function. That's the name of a function. And inside that, there are two variables, namely x and w minus px x over py. Right, it has two arguments in it, just like the parent function, and the same is true of this function. Right, and that means you've got to kind of keep in your head all the time, all the terms that are differentiable by x or by p. Right, in some cases, both terms are differentiable by x. Okay, but in this case, only the second term is differentiable by y and the price of x, and the price of y. Right, so this term winds up to be quite important when we do these comparative static exercises. So let's just turn the crank on one of these. So we want to do, let's do the p, we want to do a derivative of this whole expression with respect to px, okay? So px is in the second term of this function, in the second term of this function, and in this term, right? So it shows up in three places that we need to worry about. So this term, the first one, so we take the derivative with respect to the first term because there's no x there, so we don't have to mess with that. It's just 0. The second term, the derivative of that, the equivalent of that du dy term is dux, du squared dx dy. That's the cross partial. Okay, and then the derivative inside of that function, using the composite function rule, will be the derivative of this term with respect to px, right? And that's going to be minus x over py. Right, so that's the result of this derivative of this first function. And we do the same thing on the next one. Right, so on this second term, we're using the multiplication rule as well as the composite function when we're doing the derivatives. All right, so when the multiplication rule says is you take the derivative of the first term and multiply it times the second term, and then take the derivative of the second term and multiply it by the first term. So the first of these is this expression here. Right, this is the derivative of this function du dy with respect to price of x, right? Because it's got this term as the second one, right? That's the y location. So we're taking a derivative of this function with respect to y, and the notation for that is just du squared dy squared, right? And then we're taking the derivative of the inside, and that's the same as it was before, so it's still minus x over py. And then we multiply it times this term, because it's, it's using a product rule. That's minus px over py. And then we take the derivative of the second term with respect to px, and that's just minus 1 over py times the original term. So that whole expression is the numerator. Now, just looking at it, you might think, oh, geez, maybe I should just go home. This is too hard. But it's not that hard. Okay, once you have it, you just relax a little bit and then think your way through one term at a time. All right, so we've assumed that the cross partial is positive. This is a negative. So the overall term is a negative, right? A positive times a negative is a negative. We've assumed that this term is a negative. And we assume that that's, these x1, py is positive, right? It's a good, y is a good. X is just a number of x, that's positive. So minus a positive or a positive is a minus. The last term's two prices are positive with a minus side in front of it. So it turns out that that's a minus. If we look at this term, this is a plus. It's a, y is a good. That's a minus. That's a minus. So the whole thing is a minus. All right, so you can tell that the numerator is definitely less than 0. Okay. Now, this term can be written as simply, if you go back to the original problem, this is just du dx squared. Right? Remember, this whole term was du dx, or this is du dx, right? I need a better notation for that, but right, it's that term. But it's going to be a kind of a messy thing because of all these interaction terms. I feel it'd take more than one line to write down. But let's try to work it out this time. We do know that this thing's going to be less than 0 because the overall problem is going to be strictly concave, right? So you're just basically looking at the second derivative of the original optimality problem, and it's going to be negative if it has a nice clean result. Okay, so what's this thing look like? Let's see what we can do with it. It's good. It'll probably string around and be a bit messy, but let's see what we can look at. So each of these guys has x's in both places. So there's going to be 2 terms for each of those derivatives. And one of them is going to have the multiplication rule involved. So the first derivative of the first term is going to be du dx squared. So that one's easy. Plus du dx dy. It's supposed to be a y. And then the inside term is the same thing we had before. That's that w minus pxx over py. So when we take the derivative of that with respect to x, we're going to get that term that we've seen before. That's the px over py term with a minus sign. Right, so that's the those are the derivatives for this term. That was not too bad. And there's a minus outside all of this. So then we do the second term, and we're going to get u dy dx. Let's keep the notation consistent. Right, and that term will be multiplied by this, the minus px over py. And then we're going to have the next term, which is going to be plus du squared dy squared times minus px over py. And there would be 2 of those. Pardon me. There's just one of those for the first term, and then like that. All right. So pardon me, I lost track of myself. I'm still a little fuzzy-headed from the code, but not too bad. All right, so now we're doing, so we did the derivative of the first term, now we're doing the second term, that's this. Okay. And then we're doing the last term, which is just okay, so I'm just double checking that. I say for this one we had 2 terms, for this one we had 2 terms. Right, the first term was just the u squared dy dx. Second term is the u dy squared. And that term will have 2 of these guys multiplied together, so that's actually a squared term there. And then the last term will just be the root of this and multiplied times that, so it will be, wait a second, there's no x there. So we take the root of that with respect to x, we get 0. So there's no real multiplication. So 2 errors that I almost missed. All right, so let's see if we can sign this thing. Okay, so that's a negative, right? The second derivative, because diminishing marginal utility is negative. This is a cross partial, which I sometimes call Congleton's rule because nobody else ever mentions this convenience of having positive cross partials. Zero cross partials also are handy. They just get rid of a lot of these all these cross terms. Anyway, this is a positive term times a negative term. That's also negative, so the whole first term is negative. This is a positive by assumption. That's a negative. So that term is negative. This is negative, and this term, because it's a square, has to be positive, so that's a negative. So it turns out that the whole thing inside the brackets is negative. Meaning what? Meaning that the problem is strictly concave, like we need it to be, in order to be assured that there's at most a single x linked to every price. So the overall denominator is a negative times a negative, which is a positive. So the sign is determined by the numerator. And we already worked out that the numerator is negative. So that means what? It means that the demand curve slopes down. It has negative slope with respect to price. Well, you can do this kind of thing for the other terms as well. You can look at the effect of the price of a substitute. You can look at the price of or the effect of wealth on consumption. Those are all useful exercises. The denominators of all those problems will be the same. Okay, this is the term in each one of those cases if we want to look at how the demand function changes when the price of a substitute changes, or the budget constraint itself, the wealth to be allocated between the two goods changes. And what will change is the numerator. And the numerators will not look that different. Okay, all the action will always be in the second term, but the derivatives of this second term with respect to the other variables will be different. Okay, and that's where all the action will show up. In most cases, those can also be signed. So what's neat about this is it shows that for an extremely broad set of utility functions, it's not only easy to derive a demand function. It turns out that you can unambiguously sign them, which means you have qualitative comparative statics that come out of the results that are really clean. And although these derivatives are somewhat ugly in the sense that they have a lot of terms, and you have to kind of really focus on the derivation, okay, of them using various combinations of the composite function rule and the multiplicative rule. They really aren't that bad when you get through. They just look kind of messy in terms of the notation. And simple notations don't change the meaning of the equations. They just make it look a little bit neater. Normally when I write a paper, I use subscripts rather than the delta type notation for my partial derivatives and so forth. Probably because they're much faster to type than these guys are. And partly because once you get used to them, they're just as clear as these guys, and give you much neater looking kind of results. I use this delta notation because I assume that most of you students, are more comfortable with that at this point in your careers than you would be with the subscript type of notation that you see fairly often in published work. Occasionally you still see this delta type notation. And it helps a little bit to help to keep straight what the logic behind the various derivatives, the things that are already themselves derivatives, look like. In some ways that's not completely intuitive under the subscript notation, but seems to be more intuitive with the delta notation, which is another reason they introduced the implicit function material in this way. So give this a work, give this a try, and there's one of these problems on the homework problem set. And just take your time. Make sure you don't make any careless mistakes, and stick with it. It's not that hard. It's just it's a little bit daunting at first when you the first couple of times you turn the crank on the problem. So with that, I'll end this first lecture, which finishes up our section on the new classical theory of demand. And I'll end this recording and start another recording on the first part of the material on the new classical theory of supply.